So this is how the structure, research at IPhT is structured. We have three groups: mathematical physics, cosmology, particle and nuclear physics, to which I belong, and also statistical and condensed matter physics. And it's a recurring question since I've been here, which I've been here for quite a long time now. Does it make sense to have such a broad range of topics in a single institute and building? So I wanted to just illustrate, just testify that for me, I'm a nuclear and particle physicist, the input from statistical physics and also mathematical physics was crucial throughout my career. And for this, I need to explain the physics context, what I've been doing. So I've been working on, all my career essentially, on high energy experiments with nuclei. So high energy physics is traditionally the field which is completely separate in theoretical physics, in that you are really concerned about fundamental laws, discovering new elementary particles, not really in complexity. And the way you do this by accelerating particles as simple as you can. Electrons are the best because they are really simple. Protons are okay at the highest possible energies. But nowadays we also use accelerators to accelerate atomic nuclei, and this is what I'm doing. So it means that you take atoms, you strip all the electrons, and you collide them with other nuclei. And since nuclei are made of a large number of protons and neutrons, of course you create many particles. At the LHC now, a central lead-lead collision at the LHC produces typically on average 35,000 particles, so its complexity is back. So it's high energy physics, but it's also physics of complexity. So I'll just go briefly through the history of the field. I started my PhD in 1985 here, and the experiment started, I think, the year later. So it started with in the 20th century with nuclei that were accelerated on fixed targets of heavy nuclei. First, they did this with light nuclei, so it was done simultaneously at the Brookhaven National Accelerator. It was an accelerator called AGS, and also at the CERN SPS, where the W and the Z boson were discovered. They were discovered in collider mode, but here it was used on fixed target. It was just in one sense, to accelerate nuclei. And then a few years later, they accelerated really heavy nuclei. Lead at the Brookhaven, and gold at Brookhaven, and lead at CERN. It's still the case now. And there was a big change in the 21st century. It was actually exactly in 2000 that we had the first ever nucleus collider. So nuclei were accelerated in both directions, which means there was a huge increase in energy. And so it was a dedicated collider that was built for this purpose, which was called BRIC, which was at Brookhaven. I'll talk about it more. And exactly 10 years later, we had yet another jump in energy. That was the LHC, which is known for accelerating protons, but also accelerates nuclei every once in a while, like 3 weeks in the fall, typically. And I just show, because I'm going to show results from these experiments. So there are, yes, so this is the Brookhaven complex with the AGS, which is the smaller accelerator that was used before, and RIC, which is still in operation. And there is I show results from the STAR collaboration, which played an important role. And the CERN complex with the small accelerator, the SPS, which is 2 kilometers wide, and the LHC, which is 9 kilometers wide. And LHC has 4 experiments, and actually all of them study also. One of them was built specifically for nucleus-nucleus collision, but the other 3 also take data, and they obtain very nice results. And this field has been represented forever at IPhT. For there was the pioneers, defined as people older than I am. So there was Jean-Paul Blaiseau, who was my supervisor. Actually, so none of these people worked full-time on nucleus-nucleus collisions. So all of them produced important results at some point. So there was Roby Peshansky, Mancuro, and Madeleine Soyer, who I didn't find a picture of her on the web. She moved to the experimental department a few years after I was hired here. And there is now the younger generation, François Gélis, Edmond Yankou, Grégory Soyer, and we now have 2 postdocs and 1 visitor working with me. So all these people did very nice work. I'm going to talk more specifically about what I did. So the motivation. So the starting point was when I did my PhD was it was thought that the equation of state of QCD had a strong interactions, had a first order phase transition, and we wanted to see this experimentally. Actually, this later proved wrong. We now know that there is no first order phase transition, and it was actually an idea of Leon van Hoof, who is known as a condensed matter physicist because there is Van Hoof singularity, which I was taught in the master class. He had also been Director General of CERN, and he argued that we could measure this equation of state if the produced matter thermalizes, and he also predicted that the transverse momentum of a particle would be proportional to the temperature, so it would give direct connection between data and the equation of state, and we proved this right actually 3 years ago. So it would be a long journey to obtain this result. And the thing is, if the matter thermalizes, we know that there's physics, it expands like a fluid. And it was my first assignment as a PhD student to write a hydrodynamic code to compute this expansion and check the correspondence that had been postulated by Van Hoof. And very soon we had the first experimental data. And there was not a single hint that a nucleus-nucleus collisions was anything else than just a superposition of independent nucleon collisions. So it was what everyone was doing. It was reproducing data fine. Of course, you could not rule out that it was thermalized, but I was a bit depressed. And actually, I had a hard time believing that you could have thermalization in a system as small as the atomic nucleus. My supervisor, Jean-Paul Loiseau, was very optimistic. He told me hydrodynamics can't be wrong, and he was right. But but back then, I was a bit. I thought it was fun coding, but I didn't think it made much sense physically. And actually, I put a lot of energy into trying to rule out this hypothesis and trying to find something that could disprove it. So what we've been studying first was central nucleus collisions, which was at zero impact parameter, head-on collisions, for two reasons. Well, the main reason was actually it was simpler to calculate because you have nice symmetry, circular symmetry. So this is seen from the this picture is seen from the side. So this is the transverse plane, the plane perpendicular to collision. So in this plane, you just have a circle. And also, it's a larger system. It's easier to thermalize. But of course, when you do experiments, you don't choose. Once a theorist asked me, can't they tune the beam to do very central collisions? You cannot do that because the nucleus is too small. So in experiment, you have a superposition of all possible impact parameters, and this is what the data are mostly about. They tell you how, and you can have an idea of how central it is just by counting particles. It was important to model this, so I put a lot of energy into modeling this, and I actually found down those nice physics associated with it, is that if you have a non-central collision, you produce particles in an area which is not circular, so you break azimuthal symmetry, and if you have thermalization, you have pressure gradients that break isotropy, and so you have more, like you have smaller size, so a larger gradient in the direction of impact parameter than in the perpendicular direction, and so if the matter thermalizes, then you will have this anisotropic emission of particles, and it will also, if you didn't see it, it would be also a way to prove that there is no thermalization. But it was actually seen. It was actually at the relativistic heavy ion collider. So in 2000, it was actually the first results from this collider with the first day of data they collected, and they concluded. So they called this. It was called elliptic flow. And they conclude that there was a high degree of thermalization in nucleus-nucleus collisions. So it didn't disprove, but it proved actually that there was some thermalization. And actually, very soon, in the next few years, hydrodynamics became the standard tool for modeling the expansion of matter produced in these collisions. So I'm just going to show you what it looks like at the LHC, because it's a very nice illustration. This is a non-central collision at the LHC, recorded by the CMS detector. So the yellow tracks here, they are tracks of charged particles seen in the central detector, and you can see that they are not at all isotropic. There is clearly a preferred direction, which I have indicated by red arrow. And the colored areas, they are the energy seen in calorimeters. There is a hadronic electromagnetic calorimeter and then a hadronic calorimeter. And you see that emission of energy, this is a calorimeter, they just see the kinetic energy of particles, is very anisotropic. So it means that even though you just see this, you can guess just from the event display how what is the direction of impact of these particles. That's just for the physics. Now, where did I need statistical physics? So the thing is, when the first discovery of this phenomenon was done by correlating two particles. I thought I have experiments where I produce thousands of particles. I thought it was a shame to just correlate two particles. And it turns out that during my master course, just before we called it DOA, before I arrived here, I was taught my favorite course. We had many courses. I was actually graduated in atomic physics, so there was not much particle physics. It was statistical physics, which was taught by Jacques Duplantier, who passed away a few weeks ago, and Bertrand Duplantier. Jacques Desclozeaux, what did I say? Sorry. Jacques Desclozeaux and Bertrand Duplantier, who is still here. Sorry. And so one of the lectures was about the kinetic theory of gases and the use of cumulants to characterize correlations between an arbitrary number of particles in an interacting system. And so this actually, I knew that this existed. It was kind of in the back of my head, and it's something that really high energy physicists don't know about at all. So it was not at all in the culture of high energy physicists. And so I just did this with my first PhD student, Maïdine, who is now professor, university professor at the University of Toulouse, and Nicolas Borghini, who was my first postdoc, who is now a professor in Bielefeld in Germany. And we just, did this very generally, just applied the cumulant analysis to this specific problem, which is the analysis of elliptic flows. This is the idea: you have four particles. This is the example for four particles. You have four particles, you can group them in pairs. And so you can have a correlation between these four particles that results from pair correlations. And then you have a residual real correlation, four-particle correlation, which is what we call a cumulant. And I want to say that this wasn't important not just for me, but also for the field, because this is something that is really used by all experiments. Any Heivian physicist has knows about cumulants. It's really very standard knowledge in the field. I just give you a few illustrations. Well, there was the first observation of elliptic flow at the LHC. It was 10 years later. It was also with the first day of data at the LHC. This is the paper, which is very highly cited, and it was measured using four-particle correlation method. So it was measured using our method. And then there are dozens of papers. I just flashed to show that it's done by all experiments. The CMS collaboration, they measured cumulants of order 2, 4, 6, 8, so it's not just four particles, and also multi-particle azimuthal correlations. This is a copy-paste from the title of our paper, Alice, Atlas, so it's really used everywhere now. There was another thing that I learned also here from my colleagues, which is the Li-Yang theory of phase transitions. Actually, when I started my PhD, I was sharing my office with Thierry Jolicoeur, who is still here. He was working on lattice gauge theories, and he later turned out into a condensed matter physicist. And he told me he would explain to me many things on the blackboard, and I think I learned a lot from him. In particular, one day he was very excited because he had learned the papers by Li and Yang, and he explained to me what it was. It was pretty cool. So it's a theory of the liquid-gas transition, which is discontinuous. So we know just from statistical physics, by definition, if you have a small number of particles, partition function is continuous function. So you don't have the occurrence of a discontinuity is not something trivial. And they wanted to show Li and Yang, so it was a long time ago, before the parity violation. They wanted to show how a discontinuity emerges as the system size increases. It was a very mathematical paper, very easy to understand, but very mathematical, very formal. They said you just have to look for the first zero of the partition function in the complex plane. So I thought that was cool. I never thought I would use it ever. But then I actually kind of discovered it. I was interested in cumulants, and I was wondering what was the limit when the order of the cumulants, the number of particles that I correlate, goes to infinity. That's precisely collective effects. And I found that, well, I have a generating function. I need to find the first zero in the complex plane and kind of rang a bell. And so it was I just made the link. It was very easy. And then we wrote a paper, and it's So we just use it. I think it was the first use of this theory to analyze data. And it's also used routinely. I'm just giving you one example. It was applied to P-led collisions, but there are many other analyses. So they use the cumulants and also Liang-Zero's method. So it's also something that's known, strangely, oddly enough, in the field of heavy ions. And I mentioned statistical physics. I'd like also to explain why I also had mathematical physics was important for me. So first we did the cumulant analysis just by correlating all particles that we see. But at some point there was a hint a decade ago that you could see also hydrodynamic behavior collective effects in proton-nucleus collisions, which are very small, and then you have to do it with a grain of salt. And so it's important to separate different sources of correlations and correlate different subsets of particles, not all the particles, but you also want not to correlate a particle with itself, so there is combinatorics. And I remember I was in Brazil with a collaborator, Matt Luzum. I was trying to work this out. I tried for a few hours, and I thought, I'm not even going to try. I know someone who is going to do this, who knows this, all this better than I do. And it was Filippo Di Francesco. So I came back. I asked him my problem. He said, well, I think about it. He came back an hour later saying, I found a solution. But he was kind enough to say it was not trivial. So for me, it was been really difficult. And so I was very happy to. I never thought I would write a paper with Philippe. So it was a paper with Philippe. Maxime Guilbault, who was back then a postdoc working in the CMS experiment, who is now a professor maître de conférence in Nantes. And it's just I just flashed these two equations from the paper just to give you an idea for people who do mathematical physics. So it's a very elegant solution in terms of Young tableau and Möbius inversions, which is actually it's only just one page, but I would have been unable to find this ever. So for me, without Philippe, we would have had this method. Do I have like 5 minutes? Very good. So yeah, I just wanted to say, conclude with some more research, more recent developments. I mentioned thermodynamics in the title. So now that we know that the matter thermalizes, so we can go back to the old question and say, can we obtain the equation of state of strong interactions from heavy ion collisions? I wanted to mention this because it's something that we did 3 years ago, and I'm very proud of this result. So we know that hydrodynamics description is the standard description of heavy ion collisions, but it's not easy in a hydrodynamics of fluids, so it depends on space and time. Temperature depends on space and time. So it's not easy to have a clear measure of the temperature. What we did was very simple. We just measure the total energy, total entropy of the fluid, and we asked what would be the volume and the temperature of a uniform fluid at rest with the same energy and entropy. And so we define an effective temperature, and we do calculations, numerical calculations, and we find that the transverse momentum per particle at the end is just 3.07 times the effective temperature, which is exactly what Van Hove was speculating 35 years later. So I just say a few words of why the thermodynamics of QCD is interesting, because it's a way of seeing the quarks and gluons. You cannot see one quark or one gluon because you have confinement, but you can see them indirectly through thermodynamics. It's just for what is the thermodynamics of massless particles. They are massless particles. The density of particles is proportional to the temperature to the power cube, which is a number of space dimensions. But since quarks and gluons exist in many colors, you have a factor T cube for each color of them. And particle density is not a thermodynamic quantity, but it's very closely related to the entropy density. You have entropy is typically 4 per particle for massless particles. And so you increase, it results in an increase of the entropy density scaled by T cube, which this is a dimensionless number at high temperatures, where you have essentially free massless quarks and gluons. And this was measured recently on the lattice cube, not recently, but like 10 years ago on the lattice. This is the entropy divided by T cube, so it's a dimensionless number, as a function of temperature, and you see that there is a huge increase. At low temperature, you just have pions, low energy, you have colorless hadrons, neutral particles, and at high temperature, you liberate color, so you have an increase in number of degrees of freedom. There is no first order phase transition, but it's a quite abrupt change. And yes, so it's a field which is no longer represented at IPhT, but there was activity in this field when I was younger. And so we just put LHC data on this equation of state. So this is our extraction from LHC data. So it was we find that they are compatible with QCD, and it was, I think, the first direct proof from LHC data that you have the liberation of color, so that you observe the confinement at the LHC. And this paper made it to Nature Physics 3 years ago. Maybe I'll conclude with I have like 2 minutes. So. Very good, very good. Yeah, I just wanted well, yeah, I like to give physics talks, so just conclude as something more recent. So it was the first direct connection between data and thermodynamics, and we wanted to follow up on this. So we made another prediction, is that we worked on what we call ultra-central collisions. So they are collisions as zero impact parameters, very central collisions, but you can still have more or less multiplicity, so more or less, so the volume is constant, but you can increase the multiplicity by like 10-15%. And if you increase the density, well, you increase the temperature. So you can increase. So you can measure. If you can measure the temperature, you can measure also how it increases with the density. And this is actually in thermodynamics, derivative of temperature with respect to density. It's the speed of sound squared. So we predicted this increase. It was not. It was observed that the mean transverse momentum was constant with as a function of particle multiplicity. We predicted that at the very end it would increase. It was observed 2 months ago, so I was excited to show this result. It was shown for the first time at the Quark Matter conference, which is a big conference in my field, by the CMS collaboration. So before we only had these data, it was essentially constant as a function of the multiplicity of particles in the collision. It was a constant. We predicted this increase, which is this, the dots are the data points, so it was observed by CMS. This dotted line here is our prediction from 4 years ago. Then since then there was a better one. Gardi Metal, that's my paper. And then they went, and so here is the picture of the collision. These are, as it decreases, and at the end you have zero impact parameter collisions. And so from this they extracted just from this slope of this curve. The log slope is exactly the speed of sound squared. There is no factor, no nothing. It's a very direct measurement, and they compared it with lattice QCD, and it's the most precise measurement. It's a preliminary result, but I thought it was interesting. So, I just wanted to show something new. And that's essentially it. So I want to thank you for your attention.
Merci beaucoup, Jean-Yves. Donc peut-être des questions or comments. I can ask something naive. So, are there some signatures of entanglement between the outgoing particles? Is this visible in the correlation somewhere?
There are what is called the Bose-Einstein correlations. I don't know if this. So quantum correlations, which were very much studied in the 80s actually, because they are a way of measuring the source of the size of the source. But it's really correlating, so they are exactly two particle correlation, but with particles with very close momenta. But it's actually very interesting because I was mentioning elliptic flow, which they tried to measure in fixed target experiments. So they measured two particle correlations, and it was actually my first paper with this first PhD student, was to show that everything they were seeing was just Bose-Einstein correlations, so, which had nothing to do with thermalization. So it was a background that was then systematically suppressed just by choosing particles with not too close momenta. So, so this is the most closest I can think of entanglement. Maybe it's quantum correlations.
Est-ce que tu attends des résultats des nouveaux collisionneurs?
Quel nouveau collisionneur? Je crois que ça va. Bah, c'est le LHC, c'est un peu la fin de l'histoire. Hein. Je pense pas qu'il y ait grand chose de prévu. Alors, ça va continuer. Ah bah oui, enfin, le LHC va prendre des données avec une plus grande luminosité. En fait, et moi, comme je m'intéresse un peu maintenant à des choses un peu rares, par exemple les collisions très très centrales, ça m'intéresse d'avoir plus de statistiques. Donc ça intéresse beaucoup de gens, hein. Mais effectivement, et puis surtout ils vont faire les détecteurs vont être raffinés, si je puis dire. Et donc je travaille beaucoup en ce moment. Mon activité principale, c'est pas là-dessus, c'est sur qu'est-ce qu'on va pouvoir faire de plus avec les détecteurs plus sophistiqués qui seront disponibles. Donc oui, il y a plein de choses à faire.
Pas le micro.
Grégory.
Grégory.
Si. Ok, c'est bon comme ça? Parfait. Donc le LHC est encore censé tourner pendant une petite vingtaine d'années, entre 15 et 20 ans, donc il y a encore effectivement une accumulation de données qui va être assez impressionnante. Effectivement, après pour les collisions d'ions lourds suivantes, c'est pas à l'horizon. Enfin, c'est dans un horizon, si on prend l'échelle d'un trou noir comme horizon raisonnable, ça va. Sinon, effectivement, les projets futurs sont plus des collisions d'électrons-protons. Électrons-positrons, pardon. Et donc les prochaines collisions d'ions lourds, c'est plusieurs dizaines d'années.
Merci.
La Coupe du Monde?
Quelqu'un veut... Non. Okay, so if there are no other questions, let's thank Jean-Yves.